time we are in the middle of this lecture, okay, quick sort. I think I went over this one, and there's another version, okay, which like, the I and J, there's two index, start from the two ends of the array and going to the center. And basically, so we start here, right? Okay. So today, I hope like we finish quicksort, and in addition, I hope we can finish the another sorting algorithm called heap sort. Okay. So before we start today's lecture, I also want to bring you guys attention that I already uploaded the first programming assignment, okay, to EE class. Okay, the due date is a month from today. Okay, so that programming assignment, as I usually, use for this class is like to ask you to implement all these sorting algorithms in parallel. Okay. As I said, today we are going to finish the quick sort and hopefully heap sort. So next week we will finish the non-comparison based sorting algorithm. Okay, so then you have like everything for this programming assignment. But although I know like we haven't finished all the sorting algorithm now, but just want to give you guys enough time for this assignment. So I uploaded the test. So okay, come back to the quick sort. Okay, it will be interesting, very interesting to discuss the time complexity of this sorting algorithm. Okay, so basically, if you look at this sorting algorithm, obviously, where that pivot you choose end up, the location of the pivot at the end, sort of control the performance of this algorithm. Or put it another way, how the pivot partition the array into two parts. How these two parts, looks like, is an important factor for this quicksort performance. But before we start analysis, okay, we assume all the input elements are distinct. Okay, if this is not the case, they are better partitioning algorithm, okay, to deal with the situation. But anyway, let's assume at this moment all input elements are distinct for the ease of analysis. Okay, and again, we assume we are doing the worst case analysis. Okay, but before we start the real analysis, let's have some intuition about this quicksort performance. So if you try to list the when will the quicksort give you the worst case equation? It is when your numbers are already sorted. Okay, because every time the figure you pick, okay, it breaks the array into two parts where the first part is empty, the next, the second part is like n minus 1, or the other way around, like first part is n minus 1, the second part is empty. Okay, so this is the worst case scenario. T of n equal, T0 plus Tn minus 1 plus, this is the cost for partition. Okay, and then, okay, assuming this is theta 1, okay, constant time, and then we have this. And if we try to consider this again, okay, well, you can do this again, okay, and again and again. So eventually, okay, you are going to get like theta n squared. This is arithmetic series. Okay. Or if you try to look at it, Tn equal T0 plus Tn minus 1 plus T over C times n, and then try to look at it as like a recursion tree. Okay. So it's going to give you this, right? Cn T0, Tn minus 1. And then you keep expanding T0, okay, Tn minus 2. You have a Cn minus 1 here. Okay, and this one is stop, and you keep doing this part. Blah, 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 blah. Eventually, you keep like, you are going to have a tree like this. So all these parts, because each level, you go down each level, like n is increment by 1, right? So you have this n, roughly n number of T0. Okay, but so the issue is not about T0, okay? Because each T0 gives you constant time, so this is just like linear time. But the issue is this: Cn plus Cn minus 1 plus Cn minus 2, or plus. So eventually, this part, okay, give you n squared, okay, arithmetic series. Okay. So at the end, okay, this part accounts for these zones as well as the the first partition, and this one is like the amount of time, okay, we spend. Well, actually, for every part, for all the partition, okay. So totally, so that's worst case scenario. Okay, if you try to use recursion tree to analyze it, okay, yes, that's true. Okay. Yeah, so it's bad that, quicksort has the theta n squared, but you may wonder why do we call it the quicksort? Because like compared to, for example, merge sort, the time complexity doesn't seem to be good, right? The quicksort time complexity doesn't seem to be good. Okay. How about the best case analysis? Best case. Of course, we understand that we usually do not consider best case in analysis, okay, in complexity analysis. But let's just, for intuition purpose. Okay, let's just have a look. Okay, just roughly, assuming, some special case. Okay, for example, if we partition, every partition split the array even, that's the best case scenario. If that's the case, okay, the quick sort immediately become Tn equal to 2 times T n divided by 2 plus delta n. This one is very, we know this one, from the merge sort that it is delta n log n. Okay, it's the same as merge sort, so this is pretty good, but it comes with an assumption. Okay, the partition has to be done right. Okay, but say if we are unlucky, what I meant is like it's not that unlucky, but a little bit unlucky. Okay, every time the split is the ratio is 1 to 9. 1 to 9. That's pretty bad already, right? That's pretty bad already. You randomly pick a number from an array. I know like it is like not likely you can pick a median, but it is also very unlikely you can pick like the biggest or smallest element. So this assumption is much more practical. Okay, the split is it's not any worse. Okay, I probably should say it's not any worse than 1 to 9. Okay, then you have this T of n equal to T 1 over 10 and plus T 9 over 10 and plus delta n. Right? So how bad is this? What's the complexity of this recursive formula? It turns out it is actually pretty nice. Why? Because of course, like it doesn't. You cannot use like a master theorem on this format. It doesn't fit the master theorem format. But you can still use the recursion tree. Okay, so it becomes like something like this. Assuming the left side always has like a smaller part, the right side always has a bigger part of the split. So you can imagine, okay, each level gives you Cn, right? Each level gives you Cn. Okay, and the left side ends quickly. The right side, okay, when will this one reach delta 1? The issue is the height of the tree. How tall is this tree? Okay. Obviously, the leaf nodes, the other leaf nodes, doesn't contribute a lot of like time. The issue is each level you get Cn. So how tall is this tree? That's the important part. Okay. So we know like eventually, okay, the rightmost, okay, this branch control the height of the tree. Okay. So because each time this n gets divided by 10 over 9. Okay, this n divided by 10 over 9. It is divided by the number greater than 1, right? So, so this level actually it represents this. The height is log, 10 over 1, and this 10 over 1 is the base. Okay, and each level it gives Cn, so it's going to be Cn times dt. So the Tn cannot be any worse than this one because some part, a lot of other branches die much earlier, right? Here we assume that all the branches are available, even to this level, but it is not necessary. Well, it is not the case. It is not the case. So this is small, small equal sum, and we know that it must be greater than this one. Why? Because this one means that the leftmost branch die the first, and this height is is log 10 base, and okay, each time you go down one level, n gets divided by 10. So the time complexity is somewhere in between these two. But it is obviously unknown. I mean the big O n is useless. I mean it is it's dominated by the higher order, so this is not important. So we can see that the complexity is this one. So even for an unlucky, not so lucky case, the complexity is unknown. Okay. How about we have a lucky and unlucky alternative. Suppose we alternate lucky and unlucky. So in other words, okay, your Ln becomes, the first level is lucky, right? So it's 2 times u n divided by 2 plus theta. So this is the case where we are lucky. The next level we are unlucky, so when we get this, remember that L0 is absorbed by theta. Okay. So let's plug this one in here. Okay. Plug the un in here. So what happens that we have this. Okay. Plug that in. And this one, after that, it's absorbed by this one too. So we have this. So can we directly say it's unknown? Of course. The previous discussion are built on top of the assumptions. Okay, in the sense that this partition, okay, has a certain situation, we assume a certain situation guarantee the partition. Okay, it's not always the worst case. Okay, but based on our previous discussion, okay, is it some way that can make the partition a little bit better? How can we make sure we are usually lucky? our previous discussion, we just use the first element as here. Okay. So, we have this randomized version of the pixel. Okay. We try to partition around a random element. What do we mean? Okay. So we do not assume, okay, about input distribution. Okay. So no specific input elicits the worst case behavior. Okay. I mean, because it's a randomized selection. So the worst case is determined only by the output of a random number generator, because the random number generator determines where you select the pixel. So it is actually easier than you think. Okay. I mean, in reality, okay, there are several ways to do it. The first way to do it is, when you have an input, you first try to, do a random computation. That random computation takes linear time, right? You only need to do it once. Okay? You can still use the original pixel. Okay, and to do the rest of the work after the random computation. Okay. The other way to do it is that you can pick the first element, the last element, and the middle element. These three elements. Just pick these three elements, and then select the middle one as the pivot. Okay. Swap to the first location, and then start the partition. Okay. So this way, I mean, in the worst scenario, I mean, you will get the second smallest or second largest element, right? I mean, you have to pick three elements that contains two smallest elements in here, or two largest elements in here, but this is unlikely, right? So this is another way you can modify the pixel to make the pixel behave like a randomized pixel. Okay, so either the first approach or second approach. Okay, I believe that the textbook uses the first approach. Okay, but if you look at other textbooks, you will find that some textbooks use the second approach, but it doesn't matter. The issue is to randomize the selection of pigments. Okay? So if we assume that, okay, let's do the randomized pixel analysis. Okay? Let P of n denote the random variable for the running time of a randomized pixel on an input of size n. Okay. So obviously, we are talking about expecting the time complexity here, or what we call it. Remember, when we do the analysis of the time complexity. I mean, of course, one way to do it is the worst case analysis, right? There's another analysis I mentioned about, okay, is the average case time complexity, right? So the average case time complexity is the one that I'm talking about here. Okay? Because after all, So even for randomized quicksort, yeah, the chance to have like a worst case to happen is rare, but still, if you try to consider worst case, it is obviously still it's great, right? I mean, it's just like you are so unlucky. You pick like the smallest element as your pivot all the time, regardless how big, how randomized you select the pivot. This could happen with a very, little chance, but it could happen, right? So here we are considering like the average case. So that here is a random variable, okay? Or running time of randomized quicksort up equal, okay? So we first, okay, for k equals 0, 1 over n minus 1, we define an indicator of random variable. Xk. This xk equal to 1 if your partition generates k n minus 1, k minus 1 split. Okay, if the partition happens to be like this. Or 0 otherwise. Okay? So you can imagine, okay, the expected value of this xk would be just like a probability of like an xk equal to 1, right? You know, if you know a little bit, if you still remember what you learned from like probability and statistics, okay? 吴老师教你的不会太记得，大多数吴老师教你，对不对？在这边，所以如果你忘记了，吴老师会读我。Okay. So this one, because it's an indicator, okay? If it's not, it's 0. Okay, so it's probability of this one times 1 plus probability of not this case times 0. So obviously it's this one. Okay, so the probability for this situation to happen, okay, because remember we talked about we randomize the selection of people. So like the probability for this to happen is 1 over n. Because all splits are equally likely, right? Our randomized process assume, should guarantee this. Randomized process should guarantee all splits are equally likely. So it's going to be, if the probability for this xk equal to 1, meaning the partition generate the k n minus k n minus 1 split is 1 over n. You have n way to partition it. So each one has an equal probability. So this one is 1 over n. Okay. And your T of n, it could be this one. Okay, if it's 0 n minus 1 split. It could be this one if it's 1 n minus 2 split. And so on. It could be T of n minus 1 to T0 split. N minus 1, 0 split. If it's n minus 1, 0 split. Okay, so T of n could be any of these cases, right? It could be any of these cases. Okay, so for each of these cases to happen, okay, you have to multiply by the indicator, this xk, right? This xk indicate like, okay, in this split, which case happened? Remember, this xk indicate if partition generate the k n minus 1 split, and the 0 outlier. So each time, only one, when k is from 0 to n minus 1, only one xk will be 1. All the other will be 0, right? So, yeah, at the end, it could be any of these cases. It could be any of these cases. So you can write it into one single formula like this. That's why we need to introduce this indicator random variable. Okay, so far so good, right? So you guys agree with me, right? Okay. So we know T of n. So T of n equal to this one. So now let's try to put the expected value on both sides. Expectation on both sides. Because remember, after all, we are doing average case analysis. Okay, so for average case analysis, yeah, that's expected value, right? Okay, so we have P of n, E of expected value of P of n equal to expected value of this thing, right? Okay. So this one, okay, we can move this E into this summation because of the linearity of expectation. Okay, the expectation value of summation equal to expectation of each single term, and then add it up. Okay, this is like usually, always the case. This is always the case. It's a very like a normal operation when you go to fetch the value. So from there, the next one, you can apply E on xk and apply E on this big parenthesis, because this xk is independent from other later variables. So you apply this E on these two terms separately, and then multiply the result. Okay. And then the next step, we already know E expected value of xk. We already know, right? From our previous discussion. It is 1 over n, right? So, if it's 1 over n, okay, we just multiply this 1 over n to every terms here. Okay, and each of these terms, we can put the expected value separately. And then sum them up. So it's going to be like this. The reason, again, because we know this value already, and also the expected value of the whole thing equal to expected value of each of them. I mean, the linearity of expectation. We use that with earlier. We use this again, right? And then, okay, first, for formula, you try to, because this k is try to do this n times, and then divide it by n. This part obviously is just theta n, right? The last term obviously is just theta. How about the previous two terms? The previous two terms, you will soon find that, okay, even though, I mean, they do not look alike, but if you try to expand them, expand each of them, you will find this is that, expand value of P0 plus expand value of P1 plus expand value of P2, blah, 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 plus expand value of Pn minus 1. And this one, it is the same, okay? So we can put them together here. This should be k from 0. Okay, this should be k from 0. Okay, but this like index start from 0, start from 1 doesn't matter because I mean for those like small term, they can be solved by this linear order easily. Okay. So we have this. So far so good, right? So far so good. So this one from n 1 over n become 2 over n. These two terms are basically the same. Okay. So we have this. Okay. And here, okay, we explicitly say that these two terms, k equal to 0, k equal to 1, these two terms from here, okay, we can just assume they will be solved by theta, because like I feel like P0, P1, I mean, they are usually just like a constant, right? Okay, so the constant number of constant terms, but usually do not affect the complexity. So we put them here. Okay, so the index starts from 2 to minus 1. So why do we need to do this? Why do we need to care about the index of this summation? Because we are going to make use of what should I say, like inequality, okay, which has something to do with this index. Okay. So this is what we want to do. It's the expected value of P of n. We want to prove this one is bounded by a n log n, or a constant a greater than 0. Okay, that's our purpose. That's our purpose. So how do we do that? We prove that by induction. Okay, we prove that by induction. Okay, remember, like so far we learned 3 things to solve like recurrence relation, right? I mean, like this is obviously a recurrence relation, right? We use a smaller term to define the bigger term, right? So this is a recurrence relation, and we only know 3 ways to solve it. One is induction. One is recursion tree. This one doesn't look like recursion tree can do the job, right? Because there are too many branches. Okay. The third one is master theorem. Obviously, master theorem doesn't work because the formula doesn't fit, right? So the only possible way to do it is, well, just like recursion, induction. So we assume this. what we want to solve. Okay. So for k smaller than n, for k smaller than n, okay. I mean, first, this is an inequality that you can prove, okay, but it is outside of our discussion. Let's assume this is we already have this. Okay, but I will assign this one as one of the homework assignment for you to practice. Okay, so we can try to solve this inequality equation. Okay, so then remember how we solve the recurrence relation by induction. We try to, because these are the lower terms, right? So we can assume they are bounded by this, right? So we can replace this one by this one, according to induction hypothesis, right? So we can do this, because we assume this one. So, I mean, we assume this one when n smaller than k. When k smaller than n, when this n value is a smaller value, I mean this happens. So we can replace